Okay. Hello everyone. My name is Timur. Thank you for coming to my talk. We are going to be talking about C++20. Obviously, there has been quite a few talks this week about C++20. We are going to be talking about the kind of smaller features, like not the big headline features, but some of the smaller ones. So here's the kind of release cycle for C++20, so all the committee meetings that went into developing it, and we are now right about here. So that means C++20 is now feature complete. We have 2 more committee meetings in November and then February next year to kind of fix some last bugs, issues, and then after that, C++20 will hopefully be released. So now that we are now feature complete, it's a really good time to kind of reflect on everything that happened, kind of try to summarize what was going on. So I've been involved in the committee for about 3 years now, so I've been to all of these meetings above the red line here, and I've kind of followed this process. So what I wanted to do here is to kind of summarize some of the things that are new in C++20, but let's be a bit more specific. So if you look at the C++ standard, about 1/3 of it is the core language, and about 2/3 of it is the standard library. So what are we going to talk about today? We're not going to talk about anything in the library, okay? We're only going to talk about core language features. So now we're going to look at what core language features are there in C++20. It turns out, well, there's quite a few big ones. So there's obviously concepts, there's modules, there's unfortunately no contracts. So I'm not going to talk about what happened there. You can ask me afterwards. There's coroutines, there's spaceship operator, also known as a 3-way comparison. And those are all kind of big, interesting features, and there have been talks this week about all of these features. Now, today, in this talk, we're going to talk about everything else, right? So we're not going to talk about any of these big features. We're going to talk about all the rest, actually not even all the rest, but kind of most of the rest, I would say. So this is kind of the agenda for today. I tried to group this into basically 6 kind of categories, buckets that kind of segue one into another in a way. So we're going to start with initialization, then we're going to talk about structure bindings, lambdas, templates, const expert, and compile time programming, and in the end, there's going to be a few miscellaneous bits. So let's start about talking about initialization. So I don't know if any of you have been to my talk about initialization in C++. So I'm going to just like start off where I left there in that other talk. Quite a few things happened in initialization in C++20. Let's look at aggregates. Aggregates got a lot of love in C++20. Obviously, aggregates, as we all know, are these types which just have a bunch of public members, no private members, no virtual functions, nothing like that. And you can aggregate initialize them, right? So aggregate initialization has been around since before C++98. So we all know this stuff, right? So there's no constructor here, right? So the 3 is going to initialize the A, the true is going to initialize the B, and you omit the last one, and then that's going to be 0 initialized. Now in C++20, we are getting a new way of doing aggregate initialization called designated initializers. And that has been around in C, in the C language, since C99, so it's not really a new feature there, but we only now get it in C++20. And what this is just basically another syntax for aggregate initialization, but instead of having a list, you name the member that you want to initialize, right? And then you have the option of not just omitting things at the end, but also omitting things in the beginning or omitting things in the middle. So right here, we are initializing member A and member C, and member B is omitted, which means it gets 0 initialized, okay? So this is basically a C compatibility feature, but it turns out it doesn't work quite the same way as in C. So basically, there's a few things that you can do in C, but you cannot do in C++20. So you can't change the order. That's kind of a big thing. It has a reason, right? In C++, the order of declaration matters, right? So we have constructors and destructors. You need to construct members in one order and then destruct them in the reverse order. So order matters. So, you know, committee decided that it shouldn't be allowed to flip these around and write like widget brace.c and then later .a. The other thing you can't do with that is you can't nest them. So in C, you can nest them. You can write .c.e In C++20, you can still write .c and then brace.e, so you kind of can do the same thing. And you can't mix designated initializers with regular initializers, because why would you ever want to do that? That gets really confusing. And the other thing that I also thought was kind of not very useful is doing it with arrays, so dot and then a number, so you cannot do this in C++. Turns out this is actually useful, as I learned in Miro Kneipp's talk earlier this week. There are use cases where you might want to do this stuff, but you can't do this in C++. But still, very good, very useful feature. Right, so now we're talking about aggregates. In C++20, another thing happened to aggregates, which actually is very significant. We actually changed the definition of what an aggregate is, okay? So this is the change in C++20. So in C++17, an aggregate is a class that doesn't have user-provided or explicit constructors. In C++20, now an aggregate cannot have any user-declared constructors, okay? And that's looks like a small change, but actually, so this is a paper that I wrote, and it was very small change, but incredibly hard to get through the committee because it's a breaking change. Committee doesn't really like breaking changes. But the reason we decided to do this is because it gets rid of a very weird property that aggregate initialization has in C++17 and before. So basically what this change means is that aggregates can no longer have constructors in C++20. Before, you could have constructors that are user-declared as long as they're not user-defined. So you could do something like this, right? Where you have a struct and you delete the default constructor. So it's not user-provided, okay? And in C++17, this class is an aggregate. Clearly, the intent of such a class is not that it is an aggregate. The intent is you shouldn't initialize those things, right? If you ever write something like this, what you want to communicate to the user is you're not supposed to initialize this class. You're not supposed to create an instance of that. But because it has no members, or maybe it could have like an int member in there or whatever, not really due to the intention of the author, but just because of the way the rules worked, this was an aggregate. So which means if you say widget w1, like you try to default construct it, it fails, which is the intent, right? You shouldn't be able to do that. But if you just add curly braces, then you turn this constructor call into aggregate initialization, which completely bypasses the constructor, and now it's not calling the constructor anymore, it's doing aggregate initialization, and that's allowed, which means in C++17, this would compile. And this is, of course, not the intent here, right? So in 20, we changed the rules, and now this is going to be an error, because if you say widget equals delete, then you declare a constructor, and then it's not an aggregate anymore, okay? There's more problems with aggregate initialization in C++17. So just to name two, doesn't really work with macros, okay? So if you have a widget, it takes, you construct it, you give it some constructor arguments, that works, assert as a macro, right? But if you replace the curlies with braces, that doesn't work anymore. That doesn't compile. Because the preprocessor has a special rule, if there's a comma in there, but it's within nested parentheses, the macro has a special rule, it knows how to deal with that. But if you replace it with curlies, then that special rule does no longer apply, which means if you have a comma in there, the preprocessor will think, all right, well, brace to comma, and then that's the start of the next preprocessor macro argument, right? And then it's just completely broken, so that doesn't work. The other thing that doesn't work is you can't do perfect forwarding with aggregates, okay? So if you have these braces, you can't use them for perfect forwarding, which means you can't write an emplace function or a make unique function that takes basically arguments and then aggregate initializes something, okay? So you couldn't write make unique or emplace for aggregates, which is not nice because that's something that keeps coming up. You want to be able to do that, okay? So in C++20, we have a fix for that. You can now direct initialize aggregates with parens instead of curlies, okay? So this will compile in C++20. And this is actually really interesting, right? So there's no constructor here, and this works the same way as the curlies. And not only does it work with aggregates, it also works with arrays. So arrays are aggregates. So it works with aggregate classes and also with arrays. So you can even initialize an array with parens. And that's interesting now because there's this debate about uniform initialization with the curlies, and then sometimes it doesn't really do what you want, and it calls like still initializer constructor, which does weird things. And I had another talk where I had a bunch of examples about that. Now, we have basically with this, we have uniform initialization to 0, okay? So we have a situation where Parens and curlies do pretty much the same thing, right? So there's a few exceptions. The parens don't call a std initializerless constructor, which is now nice because now you can use the curlies explicitly to say, I want to call a std initializerless constructor, right? For a container, for example. And the other thing is that curlies still don't allow narrowing conversion, right? The way it has been since C++11. But other than that, parens and curlies now do the same thing. You can use them to initialize classes, aggregates, arrays. So they work in all these like generic contexts where you do perfect forwarding and stuff like that. And that's really nice. One more feature that has to do with initialization. So let's say you have a type, a color, okay? And then you have a static object of type color, right? So if you have a static object, you have to initialize it in a CPP file. What happens if you then somewhere else have maybe another object, which might also be a static object, that relies on the first static object? What happens? Oh, so I'm missing a static here. So this should read static color, background color. So if you do this, you have the initialization order fiasco, right? So it's undefined in which order static objects are initialized. So you might try to initialize the background color with the red, which hasn't been initialized yet. So your program is going to crash, okay? How do we fix this in C++17 and before? Well, okay, we could say, let's make the constructor const_expr, okay? Let's make this a literal type that can be constructed at compile time. If you then have a static object, the color red, and then you initialize it, because it's const_expr, it's going to be initialized at compile time, right? We call this constant initialization. If the initializer is a constant expression. The problem is, if you initialize it with something that is maybe not a constant expression, then you get dynamic initialization again, and then you're back in the initialization order fiasco, okay? So in this situation, this is kind of when const_expr came out in C++11, that confused me for quite a while because const_expr doesn't really mean at compile time. It means maybe at compile time, maybe at runtime, depending on whether you give it something that is not at compile time or not, right? And this is kind of confusing. And in this case, so in the first version, it would be constant initialized at compile time. The second version, well, that depends on whether getColorRed is a const_expr function, right? We don't know that maybe. So we still haven't really solved the problem. So how can we solve the problem? Well, of course, we can make the static object itself const_expr, okay? So if you do this, now we're fine, okay? If the object itself is const_expr, then it has to be initialized at compile time. So if you initialize it with a constant expression, it's going to work. And if you try to initialize it now with kind of a runtime thing, that is not going to compile. Yeah, it's going to say, well, I can't do that at compile time. That's good. I mean, we can do this stuff in C++17. But there's still a problem. There are cases where that's not quite what you want. So what happens if it's not a constant, but you want to change the value later, right? So let's say the problem with const_expr is it implies const, okay? So what do you do if you don't want it to be const? So let's say you have this background color, okay, and it's a static object, static background color, and you want to initialize it at compile time so it's safe, but then later you want to be able to change the value, okay? So if it's a const_expr object, you can't later change the value because it's const. And if it's not a const_expr object, well, then you're back in the initialization order fiasco kind of thing. So in C++20, we have a solution for that, right? So here, if you write it like this, the problem here is, okay, so if you initialize it with a constant, then it compiles. If you initialize it with something dynamic, it also compiles, but you're back in the problem. So what we can do in C++20 is we have a new keyword, which is called const_init. And that basically means this object has to be initialized at compile time, right? It has to be initialized, constant initialization, but it's not const, right? So if you put const_init on it instead of const_expr, it means you have to initialize it at compile time. So if you give it a compile time thing, like this literal stuff, it will compile. If you give it something that's a runtime function, It will say, nope, can't do that in compile time. But the object is not const, so it means you can still change it later. Right? So that the keyword solves this problem. So you can have something that is constant guaranteed, constant initialized, but not const. That makes it easier in certain cases to use these static objects in a safe way. All right. One more thing about initializers. We have now in CppCon 20 range-based forward initializer. So in CppCon 17, we got if and switch with initializer. In CppCon 20, we're going to get range-based forward initializer. Why is this useful? So let's look at a range-based for loop like this. Is there a problem with this code? Yes. So what can happen here is, depending on what database is doing, right? If you have get database, it returns a temporary, and maybe get users returns a reference to something in that object, okay? But because it's a temporary, then after this expression goes away, the temporary goes away, and then the thing, the get users, is now a dangling reference, and you get undefined behavior. So in CppCon 17, well, okay, then you would have to initialize the database before the loop, okay, and then it's safe, but then this database object kind of leaks into the outer scope, so you might want to put braces around it so it's in its own scope, and it becomes kind of verbose. Well, in CppCon 20, you can just put it in the initializer, okay? Just the way it works for if and switch. Okay, so that's really cool. Right, what next? Let's talk about structured bindings. Structured bindings are great, but they're a bit limited in CppCon 17, okay? So if you have something like a struct with two members, or it could be an array or a tuple, so you can destructure it, you can write these structured bindings. And here, as we know, this is like CppCon 17 stuff, right? A and B are not really objects or references, they're names, okay? So there is this object, which is the widget, which is the thing in the square braces, but it doesn't have a name. Instead, you give it a name to the parts, right? So this is what structured bindings are. But in CppCon 17, there's quite a few things that you couldn't really do with this. You couldn't have a static structured bindings, you couldn't have thread local structured bindings. So in CppCon 20, all of these things will now work. And there is an even more interesting one. So in CppCon 17, you couldn't capture a structured binding in a lambda. Okay, that wouldn't compile because it's not a variable. This is the error you would get. Capture A does not name a variable. Yeah, well, it is not a variable. It is the name of a part of a variable, which is the structured binding object, which doesn't have a name for the whole thing. But very often you want to be able to do that, right? Because you treat these names essentially as variables. And now in CppCon 20, this works. Okay, so you can now capture structured bindings in lambdas. This is cool. There's a question though, what should it really do? Okay, so what happens if you have an object like the widget? So you have part A and part B, and then you capture the A in a lambda. So there's basically two options here, right? So you capture it by value here, which means it will copy something. So the question is, should it copy the whole object? Or should it copy just the member, which is not really a variable in itself in this scope? What should it do? There was some discussion about this in the committee. We ended up with saying, well, what do you think would be the right choice here? Just the member, yes, and that's exactly what we did. So this is going to copy the member, not the whole object, which is what everyone would expect, I think. So that's a good thing. So now that works. So now that we're talking about lambdas anyway, let's talk a bit more about lambdas. Lambdas are more powerful in CppCon 20. One particular feature you can do is you can now use a pack expansion in a lambda init capture, which is very useful when you do like generic code with variadic templates. But then the two features that I'm really a big fan of are these two. So in CppCon 20, lambdas are allowed in unevaluated contexts, things like decal type, right? And lambdas stateless lambdas are default constructible and also assignable, okay? So if a lambda doesn't capture anything, then, it's essentially just, a struct with like a call operator in it. So this is now default constructible, and this is super, super, super useful. So let's look at this. So first of all, you can do this in C++20, okay? So you can take the decal type of a lambda. This is not possible in 17. Well, if you can do this, then you can use that type, for example, to declare a variable, okay? So now you can declare a lambda like that. You would say, no one does it that way, right? I mean, you would say auto f equals, bracket, bracket, brace, brace, okay? But there are situations where you cannot use auto, right? So for example, you cannot have auto for a member of a class, right? So the fact that you can write it this way now means that you can now have a lambda as a member of a class for the first time. This was not possible before, okay? You could still think, okay, well, why would you do this? But actually, this is super useful. And this comes up whenever you have any kind of object that stores something like a callback or a predicate, like a function thing, and you want a template on the type of that function thing. And it's something that actually lives in the object, and it comes up over and over again. And just to give you two examples, like, for example, the deleter and the unique pointer, okay? So previously, you would have to give the unique pointer a deleter object every time, okay, if it's a lambda. Now you can just say, well, let's declare the deleter type as the type of a lambda. So you can do that because now you can have the lambda in the unevaluated context, which is decal type. But more importantly, it's default constructible, which means you can now start initializing these pointers, and they will just, initialize this lambda, like default construct this lambda. It's all just going to work. So you don't have to give an instance of it every time. You just specify the type, put the lambda in there, and then it's going to work. Yes, there's a question. Yes. Well, if it's the same token sequence, then it will be the same type. So this will be the same lambda here. And actually, unique pointer is the implementation of it is really clever. So it actually doesn't have to store an instance of this thing in every single unique pointer, right? So it's enough to have only one instance of this thing. And that actually saves memory as well, right? So you don't have to store the deleter with every unique pointer. So you only have one of these lambdas, effectively, under the hood. So another example where it comes up is if you have a predicate. For example, you have a set where you have, or a map or whatever, where you have like the comparison thing, which is also a template argument. And you can do the same thing, right? So you can say, okay, set of a widget, and then my comparator will be the type of this lambda. And then you don't have to give it an instance of that lambda in the constructor. You can just declare it in the type, and then it will just work. And this comes up in other cases as well, where actually I had this thing a couple months ago where I came back from a committee meeting, and then I went back to my day job where I'm actually writing like code that does stuff, and then I just typed something like this, decal type lambda, blah, blah, blah. And then I was like, why doesn't it work? And then I was like, the compiler doesn't do C++20 yet. But it was just so useful. Right, lambdas, what else? What else do we have with lambdas? So we have, since C++14 actually, we have generic lambdas, okay? So if you have a lambda and then you say auto for the type of a parameter, now what this is going to do, it's going to implicitly create a template, okay? So this will be a function object where the operator, the call operator, will be templated. And then, if you give it different types, it's going to be different lambdas. So this is implicitly a template, and this has worked, since C++14. But in 20, we get this for normal functions as well. And this is kind of a fallout of concepts as a bigger feature. I'm not going to talk about concepts here. So with concepts, you can do more. But as a consequence of having concepts, so if you have concepts, you would say kind of concept auto A. But then if you just you don't name a concept, you just say auto A, then that is kind of the most general concept which doesn't constrain the type. So effectively, you've created a templated function where the parameter is just a template parameter, the parameter type, okay? So effectively, we have now generic functions in C++, which is really, really cool. So I expect, especially since we also now have, we had for a while the auto return type. So now we have auto parameter and auto return type, both for lambdas and for normal functions. So I expect people will use this quite a lot. It looks cool, it's kind of short, it does what you want. It's obvious that it's a template, right? You just have to remember, if you see the auto in the parameter, then it's a template. But it's the same as with generic lambdas. Okay, but one thing is, if you have this template, sometimes you want to have access to the template parameter, okay? So for freestanding functions, this was obviously possible since forever, right? So you can, instead of writing void f auto vector, you can just write the long form, template techname t, so this is like the traditional syntax. But what happens if you want to do this in a lambda? So we're now the other way around. So you have a lambda, which is a generic lambda, but you want to use the t, right? For example, it takes a vector of t, but then you want to like construct a t inside that function. For lambdas in C++20, we can now specify the template parameters. And we have this syntax now for that. So you have the square brackets, which say, lambda starts here, and then you can write the template argument list just after that, okay? So this declares a generic lambda, but then you can use t inside of the lambda, which is really useful. So now I think the only thing that we are really missing here to make kind of lambdas and functions kind of symmetric is to use this syntax, this kind of short template syntax on normal functions. And maybe I'm going to propose this for C++23, and maybe you're going to get it in C++23. We shall see. All right, but now that we're talking about templates, let's keep talking about templates. Let's say we have a template like this. So this is about NonTab template parameters. And we had a talk from Jeff Snyder earlier in the week about this one feature. Basically, what happens here is that sometimes it's useful to have something as a non-type template parameter, which is maybe a user-defined type. Like, for example, a chrono duration is essentially just an int under the hood. It's like a counter, right? But there's like this type around it. So it might be not unreasonable to be able to use that as a non-type template parameter. Unfortunately, in C++17, if you try to do that, it's not going to work. It's going to say, well, you can only use certain types for non-type template parameters, and chrono duration is not one of those types. Okay, so the rules in 17 are that if you want to use a non-type template parameter, it pretty much has to be either a built-in type or a pointer. That's pretty much it. So integral, enumeration, or pointer, or reference. In C++20, the rules look quite a lot different. So it's now a lot more generic. These are the rules in C++20. You can use anything as a non-type template parameter. If it's a literal type, which means you can construct it at compile time. We saw this before. It has a const_expr constructor. And if it has strong structural equality. So what does that mean? Strong structural equality. Turns out it means if the values are equal, then the types parameterized on that value will also be equal. And that's a really important property. It wouldn't work without that, because if you have templates, what a compiler needs to do all the time is it needs to verify whether the two types are the same, right? So you're instantiating some kind of template, and then you might have a primary template somewhere, you might have a bunch of specializations somewhere, and the compiler needs to figure out, well, is this type that you're trying to instantiate here, is it the same type as one of these specializations? And if not, it needs to use the primary template. So it compares types for equality all the time. And that has to be really fast and really efficient. So with integers, it's trivial, right? If you have an integer as a non-type template parameter, then a type templated on an integer is like really, really easy to compare two integers for equality. But what if you have a custom user type? How do you compare that basically two types templated on this value are the same type? And that can only work if you have a kind of the strong notion of the values are the same. So this is a long topic. I don't want to like talk too much in detail about this, but basically, the way you do this is if you have, let's say, a struct point, right? So it has 2 integers in it. So it's what you want to be able to do is you want to be able to template on a pointer. And then the equality thing is actually easy, right? So this is a lexicographical compare. So you would say 2 points are the same if x is the same and y is the same, okay? Now, this whole non-tab template parameter thing relies on the compiler being able to make this comparison efficient, right? So you can't have a situation where you have like a weird user-defined function that computes a lot of stuff, and then the result of that, then the compiler can determine based on that whether 2 types are the same. That's not going to work. But with this, the compiler can generate that itself because it's really easy to figure out how to compare points. And so in C++20, we have the spaceship operator, we have three-way comparison. Again, I'm not going to talk about this in this talk, but one consequence of that feature is that you can now default the equals operator, right? So you can do this with your type. And if you do this with your type, then the compiler will say, okay, well, I'm going to generate the kind of lexicographical compare. And then basically you can directly compare these 2 pointers, these 2 points, and the compiler will just generate this thing which says, okay, operator equals is x equals other x and y equals other y. It's going to just generate that for you. And as soon as you have that, you can now template on that point, right? You can use that point as a non-tab template parameter. And that's really cool. That opens up really interesting patterns where you can basically use values within the type system of the compiler to do really cool stuff. Right. So a few questions here might be, well, can I now use float and double as non-type template parameters? Because this is something that people have been asking for many years. Turns out, well, no, they don't have strong structural equality, okay? So comparing 2 floats is kind of weird, right? So you have things like none, which are the same value, but they don't compare equal, and other weird edge cases. So there is a way to define a strong order on floats, which is actually defined in the IEEE standard, but it's kind of weird. There would be a way to make this work. Like, for example, I mean, we already have this in like atomic float. You have like compare exchange. It has to compare floats there, but it does like a bitwise comparison essentially. So which is not what you want, right? Because like -0 and 0 compare equal, but then bitwise they're not equal, and you have all these like weird things. There was actually a paper at the last meeting in Cologne where it was proposed that we might do something like that to allow floats as non-type template parameters, but basically the paper got rejected because it was last minute. It was like too late. It was after the feature freeze. So this is not going to happen. Which I think, is not a bad thing because it's not intuitive how this should work. Maybe we need a bit more time to figure this out. And the other question that comes up, can I now use strings as non-type template parameters? Because this is the other thing that's really, really useful. Right? You want to be able to template on names. And it turns out, well, std string, not really. You can't do that. But you can write your own fixed string type, which has this defaulted equals operator, and then it works. So in principle, you can do it. We just don't have a string type in the standard library that allows you to do that. You would have to write your own. But it's super useful for things like reflection, for example, where it will come up, where you will need compile time string. All right, let's talk about CTAD, which is another template-related feature, which has been around since C++17. CTAD stands for Class Template Argument Deduction. So I have a whole talk about class template argument deduction from last year, but just very briefly, it's this feature that allows you to omit template arguments, okay? So you can say vector v, and then you give it a list of ints, and it's going to figure out, well, you're trying to make a vector of int. It works with tuple, pair, so you don't have to write like a long parameter list anymore. You don't need the make functions anymore, like make pair and make tuple, so you have this like much shorter syntax now. Certain cases where there's like really, really long type names that you would have to write out, that you don't have to do that anymore. So that's a nice feature. It's been around since C++17. But it was kind of incomplete. There were cases where CTAD wouldn't work. And we plugged some of these holes in CppCon. Specifically, yeah, now you can have CTAD for aggregates and CTAD for alias templates. So look at this. Let's look at this. So if you have an aggregate template, okay, we're talking about templates here. If you have an aggregate template like the simple kind of pair-like class, you would expect that this initialization would work, right? So you have a pair of t and u. It's obviously an aggregate. If you initialize it with t for int and u bool, then it should give you a aggregate pair of int and bool, right? This is how CTAD should work. Except unfortunately in CppCon you would get an error because in CppCon CTAD looks at the constructors that you declared, and an aggregate doesn't have any constructors, so there's no deduction candidate. So this doesn't work. So the rule in CppCon was if you have an aggregate and you want to do CTAD with aggregates, you always have to write your own deduction guide, right? So that was the rule. Aggregates always need user-defined deduction guides, which is kind of boilerplate and unnecessary because the deduction guide will always look like this, right? It's a very obvious thing. So in CppCon, the compiler will generate that for you, okay? And the other thing that CTAD can do in CppCon is CTAD on alias templates. And this is, again, very useful, and people are actually surprised that it doesn't work in CppCon. If you have an alias template like PMR vector, well, then CTAD will just work on those as well. So now you don't have to write PMR vector int. In CppCon, you can just write PMR vector, and it's going to deduce PMR vector int exactly the same way it did for the vector in CppCon. So that's really cool. Okay, so now that we're talking about templates, let's talk about const.exp and compile time program. So there's things you can do in const.exp world and things you cannot do in const.exp. In CppCon, there's a lot more things you can do in a const.exp context. So in CppCon, if you are in a const.exp context in a function, you can now have a try catch block in there. So you can't actually throw exceptions at compile time, but you can have the try block in there. You can have assembly in there, as long as you don't actually evaluate it at compile time. We're going to see something more about that later. You can use a union in a const.exp. You can call virtual functions, right? So you can have virtual functions and inheritance. And this works in a const.exp context whenever the compiler can actually figure out what the actual type is. And then this will all just kind of collapse away, and compiler is going to do the right thing. And you have const.exp new and delete. And that is really, really powerful. So that allows you to do things like implement a const.exp string, a const.exp vector, and other const.exp structures. And that kind of leads us to all these tools that we need if you want to do reflection, which is going to be, I expect, kind of the headline feature of CppCon, right? And if you want to do reflection and code generation, we need all these things. We need dynamic containers at compile time, strings at compile time, all these things. So all these tools are now in the language. And unfortunately, I don't have time to go over these in detail, but I don't have to because there's other talks, specifically these two talks by these two people who were very, very much involved in these features and have written many of these proposals and have done brilliant work in this area. So it's David van der Voorde in his keynote from CppCon Now this year, and Louis Dion's talk last year at this conference, where they go over these new compile time features in a lot of detail, and I encourage you to watch these talks. We are going to talk only a little bit more about compile time programming. Let's look at something simple, like let's say we want to compute the square of a number, okay? So this is kind of boring. We can obviously do this at compile time, right? So this is stuff that you can do at compile time, obviously. This was possible even in CppCon 11. Again, const.exp has this weird, confusing property that it might be at compile time, it might be at runtime, okay? So if you write a function like this, and you call square 3, that's going to be evaluated at compile time, because 3 is a compile time literal, okay? If you give it an x, which is initialized at runtime, then this function will run at runtime, okay? This is nothing new. This has not changed since CppCon 11. But sometimes that's not what you want, okay? Sometimes you want to say, I don't want there to be runtime cost here, right? I don't ever want to make this computation at runtime. So the danger with const.exp is you can do this accidentally, right? You can write a function that's meant to be a compile time thing, but then if you give it something that's not kind of known at compile time, it will just silently generate code that will actually run at runtime, which is maybe not something you want to do. So in C++20, we have yet another keyword called consteval, which basically says this function has to be evaluated at compile time. So we have quite a few of these keywords actually accounted. So in C++17, we have 5 keywords that start with the letters CO. In C++20, we have 11 of them. So we added quite a few new keywords that start with co or const something. Consteval is one of them. The original plan was to say const expr exclamation mark, like really const expr. Committee didn't really like that, so we changed that to consteval. Yes, there's a question. Yeah, I don't understand the question. Do we have a microphone? And also, just kind of disclaimer, I'm completely blinded by the slide. So if there's any arms in that area, I'm not going to see you.
Okay.
Really.
So could you already force evaluation at compile time, not on the function, but on that square x line? Because when you bind that to a variable, you might mark the variable as constant.
Well, sure. You can say const expr x, and then initialize it with something, and it will fail there if that's not compiled.
That line as is doesn't do anything.
Well, it depends on how you initialize x, what x is. Right? So if x is a thing that you get from like std in, then probably it's not going to be at compile time.
Then it's for sure runtime.
Yes. So that's the point. Like with const expr, it can be either compile time or runtime, depending on where the argument came from.
Okay, but you can already force it to be compile time by taking the output of it and binding that to a const expr variable.
Sure, but that's the client code, right? You force the compile time thing where you call it. But with consteval, you can force the function itself to be not actually a function. It's not actually a function. It's going to be just this kind of compile time thing. And you, if you use consteval, you are guaranteed that this will never generate any code, okay? So that's, maybe I didn't make it very clear. So consteval will never lead to a function that actually generates code that has an address. It can only ever be used at compile time, and then it kind of all falls away. And you only use the results of these functions in things like template parameters or decal type or whatever. But consteval basically means they will never lead to actual code being generated at runtime and run at runtime. So that's how you use it. Okay? Cool. But sometimes there are things that you can only do at runtime. Okay? So for example, we have the square function. Let's say we had some kind of magic intrinsic that can compute the square. That's like contrived, okay? But like real examples would be like longer, so I just came up with this kind of very contrived example. Let's say you have a square function that's really, really fast, where there's like a particular intrinsic on your CPU that computes the square in some kind of magic way. So, I mean, we have this with inverse square root, for example, things like that, right? That's where it's actually a thing. So you have a compiler intrinsic that does that. Now, this is a CPU instruction, basically, right? So it can never be something that runs at compile time. So if you have this, then you lose your const expr, right? So at runtime, you have this fast computation, but then if you give it the literal, which should be evaluated at compile time, it will actually then also be evaluated at runtime, generate code. So you can say, well, okay, I want to use this at compile time, so you can put the const expr back, but then you have to go back to the kind of slower normal implementation that doesn't use this magic intrinsic. So what you kind of want is both, right? You want to say, whenever it's at compile time, use the thing that works at compile time, so where you just have this expression I times I. But then when you're at runtime, please use the magic fast intrinsic, okay? And C++20 has a feature that lets you do that, which is called that is constant evaluated. And that thing is true if you're running at compile time, and it's false if you're running at runtime. And this way, and the standard library will be using this under the hood, I guess, everywhere in all these like math functions which are now const expr. So you can say if it's constant evaluated, well then do the normal thing, which might be slow, but we will never do this at runtime anyway, so we don't care. It will never actually lead to that code being generated. But then if you are running at runtime, then please use my magic fast intrinsic. And this will give you what you want in every case. And that also allows you to make the whole thing const expr, but then still run it at runtime with the magic fast version of it. So, is there a question somewhere? Yes, what's the question?
Is there an option to overload the constant and Constanteval with two functions instead of this evaluated?
Well, that's what you had to do before. Like you would have, but you would have to give it different names because you can't overload on the const expr-ness. You can't do that. No, you would have to have two functions with different names. So this kind of solves that problem. There's usually another question that comes up when I show this slide. Let's see. Thank you. So the question is, why do you write ifs that is constant evaluated? Why don't you write if const expr? That's an excellent question. Can you see this? If you would write if const expr, it would actually be wrong. Okay? Because if you are inside an if const expr, you are always running at compile time. Because if const expr is evaluated at compile time. Which means if you have if const expr still is constant evaluated, it would always be true. So that would not work. So you have to put it in a normal if. Okay, and if you just use this pattern, it's going to do what you want. And basically at compile time, and whether you're at compile time or not, in this case, depends on where you're coming from, right? So in the standard, we have this term now, manifestly constant evaluated, I think it's called, which means you are in a context that has to be evaluated at compile time. For example, you're evaluating a NonTab template parameter, or you are inside a decal type, or other things that you specify an alignment requirement, for example, for some type. So these are all contexts that are evaluated always at compile time. And whenever you're in one of those contexts, if is constant evaluated, it's going to be true, okay? And then once those branches all have been evaluated, you're done with compiling your program, and then the compiler can just optimize away all this if-else, this proof just goes away. And then when your program runs, you're left just with the branch that is the else branch. Okay, so this feature also has no runtime overhead either. Okay, any more questions about this particular feature? See none? Yes, there is one. Ben? Yes, please use the microphone. If it's a short question, I can repeat it. If it's a long one, it's better to use the microphone.
So it looks like with this construction, we're back to the situation where nothing's actually forcing the compiler to run this at compile time. So I would still need to make sure it's evaluated in context by signing into a context variable.
Well, it would just kind of automatically do what you want, right? So whenever you are evaluating a variable that is a const expr one, then you would run the first branch. And whenever you have to run a compile time, because you are already running your program, you would take the second branch.
It would come out right if I were running it at compile time.
Yes.
As I'm reading this, there's nothing forcing the compiler to evaluate square through at compile time.
Well. Huh. Well, I guess
Unless
that's...
the compiler magically looks in the function and sees it's constant evaluated and knows then that it needs to.
That's interesting. So if you are evaluating square 3, then it's const expr, right? So the compiler knows that you are evaluating this at compile time at that point.
It's available at compile time.
Yeah.
I don't know that anything's forcing it to be evaluated at compile time.
I think it does, but I am not sure exactly what the rule now is. So why don't we take this offline and look into the wording? I'm pretty sure that what happens here is the thing that you want, but I'm not entirely sure how the rule exactly works in this case. Like if you're coming from a kind of manifestly constant evaluated context where you're like inside a decal type, Like that's easy, right? It's always going to be the first branch. But what you're saying is like it's something which is just code inside a function body, but then you happen to give it a literal. Is it guaranteed it's going to take the first branch? And I'm not exactly sure how this rule works. So yeah, I'm pretty sure you're going to take the first branch, but I don't exactly know how this rule, what the rule exactly is. So let's talk about this after the talk. Thanks for bringing this up. All right, so I have 10 minutes left. So just about enough time to talk about a few more kind of little miscellaneous things. Okay, let's go back to templates. So here's a not really interesting template, function template, which is templated on some container type, and then it basically takes the container and then returns the first element of the container that's valid. Not really meaningful, but is this code going to compile? Okay, so forget about the function body. Yes, it should be find if. Okay, function body is not important. Yes, there is a missing type name. So, but the compiler already knows this, right? So if you do this, the error you get is error missing type name. Okay, so there's quite a few contexts where the only thing that could be in that position is a type name. Like, for example, here we have a trading return type, right? You cannot have a non-type name in a trading return type, okay? So the compiler already knows that it's a type, but because of the rules we have before, you still have to put a type name in there. So C++20 relaxes these rules and basically says whenever you're in a place where there can only ever be a type name, you don't have to write the type name anymore. So in 20, this will compile. Great, yay. So this saves you a lot of typing, it saves a lot of people fixing unnecessary compiler errors, because it's not really adding any information in this case if you write type name. Okay, what else? We have a bunch of new attributes. So we have likely and unlikely to indicate to your branch predictor kind of which branch you think is more likely to be taken. I actually learned this week that it doesn't always lead to generation of better code. Sometimes it actually leads to generation of worse code, so be careful with that. We have another attribute which is really cool, which is no unique address. So this is about what we had before as empty base class optimization, right? If you inherit from a class that is empty, then that wouldn't take up any space. Okay, that's the empty base class optimization. But that wouldn't work for members. So if you have a member in a class that was just an empty struct, then the standard said, okay, well, it still has to have a unique address because every object has to have, every member has to have like its own address. So it would still occupy like a byte of memory, even though it's empty, which is kind of, or even more, like because you have an alignment, right? So if the next member is like a float or a double, then you actually lose 8 bytes. So in 20, we have this attribute no unique address where you can tell the compiler, well, this is an empty class member, so you know what? It doesn't have to have its own unique address. So then you basically get empty base class optimization, but empty member optimization, right? So this is really cool. And then we have an attribute that we already had before, which is no discard, but it gets 2 new superpowers in 20. The first one, you can stick it on constructors now. And the second one, you can now give it a reason. So for example, if you mark a function with no discard that returns a pointer, and then that pointer would be leaking if the callee side doesn't do anything with that pointer, you can put a message on the attribute saying, well, if you hit this error, then you're leaking memory, don't do this, which is really useful for like self-documenting code and avoiding bugs. Another feature which I really, really like is using enum. So let's say we have an enum class, which is obviously better than an old-style enum. The problem with enum class is you always have to write the class name, which leads sometimes to a lot of boilerplate. Like for example here, let's say you have this enum, which is like red, green, blue, alpha, and then you want to use these values. Excuse me. You always have to repeat the enum name, colon, colon, which might be quite long. So a lot of people say, well, this is too much boilerplate. I don't want to write this. So they go back to using old-style enums, which is obviously not good because they're less type-safe. And So in CppCon, you can say, well, using enum, blah, 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 and then you don't have to do this anymore. And this is really, really cool. So this is actually more powerful than if you do like using function or something, because it actually also works in class scope. So if you have like an enum, for example, and then you want to use the value of that enum somewhere for a member, you can just use, say, using enum at class scope, and then it's just going to be in the whole class. And this kind of, it's pretty much like using namespace, basically. So if you think of an enum as a namespace with like constant integers, integer constants in it, then this is the equivalent of saying using namespace, except you spell it using enum. And that's really, really cool. So you get both the benefits of the safer enum class and the kind of less boilerplate than before. Okay, and then the last thing I have in this talk is this. So, you know, we had now for a while Unicode literals, but they're not really, in C++17, they're not really usable, okay? So you can have one of those Unicode literals, and you can store it in a const char pointer, because the char pointer can alias anything, so it's not a compiler error. But what does that mean, right? Depends on what the system encoding at this point is, right? So might be UTF-8 on some systems. It's certainly not going to be UTF-8 on Windows. So this is going to create a char array and then store some garbage in it, which you can't really rely on this doing anything useful. So in CppCon, this is not going to compile anymore, which is good because it's, you know, pretty much not useful. And what we have instead is we have a new built-in type, which is char8t. Right? So that's super cool. So this is now actually going to do the right thing. Then there's also in the standard library, there's like a U8, still U8 string, a still U8 string view, and all these things. So now you can actually properly use this. The only thing you cannot do yet is there's no IO stream support for this, so you can't get this stuff into your program or out of your program. But as long as you're inside your program, you have proper UTF-8 support and a proper type for that, and that's actually really nice. All right. So this is all I have. Again, we are here. We have 2 more committee meetings where we can't really add any features anymore, but we can you know, fix some bugs that we know we have to fix. And then hopefully early next year, this is going to be released as a new international standard. And you're all going to get it in your compilers, and you all can use all this cool stuff, and everything will be awesome. And that's all I have. Thank you. And I believe we have 2 more minutes for questions.
Slide 105.
Slide 105. Yes.
As I understand that using survives until the nearest closing curly brace, correct?
Yes.
Going way back to your color example in the first section, can you possibly bring that slide up to about, I don't know, 40, 50, somewhere in there? Sorry. Color, oh yes. Right, yeah, back, yeah, right there, for example. I'm not sure if I'm understanding what you mean by the static in the .h file, and then the color, background color in the CPP file. How are those related?
Well, it's the thing where if you have a static object, you have to declare it in the H file and like initialize it in the CPP file. That's what you have to do for static objects if they're not const_expr, right? Okay, not in the global scope. Yeah. So this is in a namespace. I should maybe fix the slide. Okay.
On this same slide, the bottommost line means invocation of the assignment operator.
Yes.
And that operator is not defined.
Not declared. Okay, sure. I mean, I've left out some of the stuff. It's not like, it's not supposed to be complete. It's just like to illustrate that you have a static object and you want to assign something to it later, but if it's const_expr, then it's constant and you can't do that.
And the color has 3 member variables, so all 3 have int type? that what is meant here in the second from the bottom code line. When the function returns color,
Yes.
the color is copy constructed,
Yeah.
and
I mean, this has nothing to do with const init, right? This is, I'm not sure if we need to take this apart further, this particular code snippet. So my point is that you have this new feature, which is const init, which lets you say something has to be constant initialized at compile time, but you can still modify it later. This was kind of the point of this. I might have omitted some things that would make this other code correct. So apologize for that.
Hi. So we saw how we have the short name to promote a function to a template by using auto.
Yes.
I'm wondering if it's mutually exclusive to the old form. So let's say we have 10 template parameters, and only the first one is one where I want to use T again somewhere else. The others maybe you could just leave as auto.
Oh, okay. So you're saying template type name T, type name U, and then for the U you want to use auto, and for the T, yeah, you can't mix them like that. It's like different, like the long form syntax and the short form syntax kind of. Yes.
47.
47.
No, backwards. 45. I assume that the function getWidget returns widget.
Yes, that is correct.
Does it matter whether it returns by value or by reference, or it doesn't matter?
Well, it doesn't matter for the capture because the capture is by value.
Okay.
So it doesn't matter for the purposes of this example. But it will obviously do different things. So it will, if you return by value, then it will do different things in the line which defines the structured binding. But that hasn't changed.
Question on this. So with today with structured bindings, you can't use like material representations. Like you try to return like a moving object by value, it doesn't work if it says structure. If it's coming from structured binding.
Okay.
Is there like anything that is there as well?
Not that I know of, no. But maybe we should fix that. Okay, any more questions? If not, then thanks again for coming and enjoy the rest of your day.